involves the synthesis of building blocks. IR spectroscopy is really the first technique you want to be reaching for when you run your reaction. IR spectroscopy is good at identifying functional groups. And for the most part, when you are running a reaction, you're doing something that involves changes to functional groups. You're adding a nucleophile to a carbonyl compound, and it's going from a ketone or an aldehyde to an alcohol. That's a huge change, and this is the sort of stuff that IR shines at telling us about, and to some extent NMR doesn't. I want to give you an example from my own graduate work that was just a revelation. It's basically realized every experiment you're running is testing a hypothesis. You have an idea. And the question becomes, what actually happened? So I was running a reaction. I expected this to just be a simple aldol reaction. I had thiophenyl acetate, and I wanted to do an aldol reaction where I treated it with LDA, and then treated it with cyclohexanone, and then did an aqueous workup with H3O+. And what I expected to get, of course, was the aldol product. And what I got instead was a product with a really strong band in the IR at 1820 wave numbers. And I knew my data was screaming at me, because the reactant, you should be running your reactants, IR and NMR. You should be using your chance to do chemistry to educate yourself. The reactant, the thiophenyl acetate, has a band, a carbonyl band at 1710. And so you'd expect the product to have a band at 1710 for this, and maybe an alcohol band at about 3350. And this thing was honky mute. I mean, it was tremendous, and 1820 stands out like this sort of thing. And I knew exactly what it was right away, and I thought, this is really cool. And it turned out this ended up being the basis for the rest of my dissertation and a patent I filed on the work. It was a discovery, and that was cool. What had happened was, under the reaction conditions, even at low temperature, it cyclized to form a beta-lactone. Not surprising in hindsight, but unexpected, and actually a compound that was way more useful than the aldol product. And so that was cool. IR can tell you that type of information in an instant. Now, all right, I want to talk a little bit about how IR works today. And then I want to talk a little bit about my recommendations on running IR experiments, because I want them to be easy for you to run. Again, my take on things for theory is very, very basic. It is like an organic chemist, because that's what I am. And the theory is basically that we're looking at transitions between quantized vibrational states. All of your molecules are going to be in the ground vibrational state, and you're going to be exciting them to the first vibrational state. The most important vibrations are stretching vibrations. And stretching vibrations are exactly what you'd expect. You'll have a bond, and it stretches. And remember, think back to PChem, 0-point energy. Even in the ground vibrational state, your bond is vibrating. If I want to represent it in very simple language or simple diagram, I can say here's a CH bond, and it's not static. It's getting longer and shorter. And what's happening is when it absorbs a photon, you kick it up a notch, and it vibrates more quickly, and you're looking at that photon getting absorbed. All right, one thing, and this is really of practical importance, is that while we can think of a bond as an atom connected by as a ball connected by a spring to another ball, right? Your basic quantum mechanical harmonic oscillator. What's happening with many vibrations in a molecule is they're coupled. And there are practical implications of this. And I'll show you one example today and another example when we talk about anhydrides. So, okay, so CH2 group, not very exciting. Not a really hot functional group. The CH2 group, you end up having two vibrations associated with it. One is a symmetric stretch. At 2850 wave numbers. And by a symmetric stretch, I mean if my body is the carbon atom and my fists are the hydrogen atoms, we're talking about a motion like this, where the two are moving in concert. And then another stretch, an asymmetric stretch. At about 29, 25 wave numbers. And so an asymmetric stretch means one bond is getting longer while the other is getting shorter. And you have this kind of inserted motion. So most of what you're going to be looking at, just because it's in what we'll talk about as the functional group region, are stretching vibrations. Also of importance are bending vibrations. And by bending vibrations, I just mean a scissor motion where the bonds aren't getting longer and shorter. And again, you get coupling between these motions. So for example, on a CH, I'll just diagram this on a methylene group. You can imagine this sort of as a scissoring in and out, like so forth. And here you're also going to have two. You're going to have an in-plane bending at 1465 wave numbers and an out-of-plane bending at 1380 wave numbers. And this is below the main functional group region, so you're not going to be paying a heck of a lot of attention to it. All right. There's a really important principle, and you'll see the practical implications of this in a second. For regular IR spectroscopy, not Raman spectroscopy, which actually is covered in the newest edition of the textbook that I am currently in the process of reviewing, for regular infrared spectroscopy, an allowed transition, the transition that you can observe, has to involve a change in dipole moment. So let me give you a really simple example, which you will actually see inadvertently as part of your work in the course of using an FTIR spectrometer. So carbon dioxide. Carbon dioxide, just as I said, on coupled vibrations, you're going to have coupled CO stretches. So you have, here you have a really big coupling. The symmetric stretch is at 1340 wave numbers, and the asymmetric stretch is at 2350 wave numbers. Normally you don't have so much coupling. So remember, the symmetric stretch is like this, and the asymmetric stretch is like this. which one of these stretches actually has a change in dipole moment? Only the asymmetric stretch. So the 1340 stretch is inactive, and the 2350 stretch is active. And the practical implications of this is if you're using an FTIR spectrometer and you go ahead and you put your sample in the cavity, you're putting carbon dioxide in the cavity, and you will actually see little bands, and with CO2 you'll actually see the rotational fine structure, but you'll see this little fuzziness at about 2350, and that's your breath. That's the carbon dioxide component of your breath. So the other practical implication of this becomes for functional groups. So if you take something like an alkyne, and so let's take as our example 2-pentyne. So normally you would see a carbon-carbon triple bond stretch. And 2-pentyne isn't exactly symmetrical, but it's pretty darn close. And so you are not going to see the carbon-carbon triple bond stretch. So what does that mean? That means if you're saying, oh, I'm looking for an alkyne in the IR, and you say, well, I don't see a band at about 2100 in the IR, so I can't have an alkyne, you're going to be wrong because you're just not going to see it because that stretch is for all intents and purposes not active because you don't have change in the dipole moment. If you go to a terminal alkyne where now you have some dipole to the bond, right? The CH2 group, an alkyl group, is an electron donor. So this end of the alkyne is going to be a little more electron rich than this end. So I can designate this as delta minus and delta plus. Now, when that CC triple bond is stretching, you're actually changing the dipole moment. Why do you change the dipole moment? Well, you have two partial charges. And as you increase the distance between them and decrease the distance between them, the dipole changes. So when you excite it to the first vibrational state, or the first excited vibrational state, you get a change in dipole moment. So here you do see the CC stretch, the C triple bond stretch, seen at about 2120 wave numbers. And I'm going to say it's sort of moderate in intensity. Carbonyls really stand out at you. That beta-lactone I gave you as an example was the strongest peak in the spectrum because you've got a really big dipole for a carbonyl, and it's even bigger for beta-lactone because of polarization of bond. But here you're going to have a weaker stretch. All right, another example, if I put on my alkyne, if I, let's say, have an alkoxy alkyne, so let me take methoxypropyne. So which way is this triple bond going to be polarized? Which end is going to be more electric, with more negative charge on it? This end. Right. Think resonance. Think like an enol, because it's just an alkyne version of an enol ether. Okay. So the oxygen's pushing electron density in, so you write a resonance structure like this, kick in here, so you've got a delta minus and a delta positive. So here again, you're going to see it, and this is actually strongly polarized. So this will be strong. So IR spectroscopy really can talk to you about what's going on in your molecule. And it's certainly in the example I gave, talk to me. All right, I want to take a moment at the very simplest level to discuss part of the theory, and that's simply the effect of bond strength and mass. I'll show you a couple of practical examples. So if you think back to your P-Chem, and you think back to your harmonic oscillator, your quantized quantum mechanical harmonic oscillator, you probably saw a diagram that was something like this. You have two masses connected by a spring with force constant K. Everyone seen something like that? Oh. And you probably remember a solution that involved the term reduced mass. Does that strike horror in the back of your mind from P-Chem? All right, so if you solve this oscillator, you get that nu bar, that's your frequency in wave numbers, is 1 over 2 pi c times root k over mu. Mu is the reduced mass, k is the force constant, and mu is equal to m1, m2 over m1 plus m2. I'll talk more about nu bar in a second. I'll talk more about wave numbers. But I want to give you a very, very simple practical application. I want to tell you the whys of why I'm telling this. So you take a CO single bond, and actually let's start with a CO double bond. You take a CO double bond, right? The carbonyl is going to be at about 1700 wave numbers. So I'll put a little tilde up, a little squiggly to indicate that that's about. Now, off the top of my head, I might not know, or for the purposes of this course, really care a huge amount where a CO single bond shows up, except I might want to know, is it in the functional group region? And so I'm going to tell you where it typically is at, and it varies a little bit, but about 1100 wave numbers. And you look at this ratio here, and you say, okay, what's he saying to me? He's saying if you double the force constant, you increase the frequency not by a factor of 2, but by a factor of the square root of 2. And so it makes sense that a single bond isn't going to be half of a double bond in its frequency. It's going to be about 1 over root 2. If I had 1200, it would be 1 over root 2, and single bonds vary here. So I'll say I'll say approximately 1 over root 2 here. Now, why is this important? Well, let's say we talk now, instead of about a carbonyl, about a carbon-nitrogen double bond, and you'd say, well, I don't know that much, but I know that, I haven't seen imines, or I haven't worked with imines, but I know that the reduced mass of nitrogen, once you plug in here, right, because you've got 12 and you've got 16 for oxygen, or 14, and you've got 12 and 16 or 14, the reduced mass isn't going to differ by a heck of a lot. And the bond strength isn't going to differ by a heck of a lot, because carbon-nitrogen bonds are pretty similar. So you'd say, okay, now, even if I didn't have a table, even if I didn't have a lookup, I could say, imines are going to be somewhere here. And conversely, you could say, okay, where's my carbon-nitrogen single bonds going to show up? Well, they're going to be somewhere about here as well. And so you can bootstrap on information with just a little bit of knowledge. And I think that's one of the really, really important things. I'll show you another example. Show you another example. Let's take chloroform. Chloroform's a common solvent for running IR spectra in these days. Cl3CH, and I'll tell you that it's at about 3020 wave numbers. And so, okay, if you want to be lazy, it's not a crime to be lazy. If you want to be lazy, because as I said, you should be getting an IR spectrum, not saying, oh, well, I'll get it when I write the paper and do my thesis and do my orals and characterize things. This is a question you're asking. So, okay, you want to be lazy and throw your NMR sample in an IR cell? and you don't even want to dissolve it up, and you say, okay, where does Cl3d show up at? Okay, well the force constant is going to be the same, so it's just the reduced mass that's changing, right? So mu for CH, and I'm not going to use exact numbers, I'll just say 12, plus 1 instead of 1.007, whatever it is. Over 12 plus 1 is the reduced mass for a CH bond. And for a CD bond, the reduced mass is 12 times 2, right? Deuterium's the heavy hydrogen. It has an extra neutron in there. Over 12 plus 2. So here we have 12 thirteenths, and here we have 24 fourteenths as our numbers. The force constant is going to be the same, so you can take this equation, you can back out the force constant in the 1 over 2 pi c term, and you get that nu bar CH times root mu CH is equal to nu bar CD times root mu CD, right? That's just from saying, all right, we're going to back this out over onto this side and equilibrate and put the two halves in. So we get 32, we get that 3020 times root 12 over 13 is equal to nu bar CD times root 24 over 14. So I would predict that the number for our CD stretch, the wave numbers for our CD stretch, is at about 2216 reciprocal centimeters. And that would be a pretty darn good prediction. I mean, remember, this idea of treating this as an isolated mass, just the carbon without coupling to the chlorines, is an approximation. The actual is about 2250 wave numbers. So if you end up throwing your sample into your NMR sample into an IR cell and taking a solution phase IR, and you see a peak from the deuterochloroform, that peak is going to be right at about 2250. And so don't say, oh, I have an alkyne, or oh, I have a nitrial, which is another thing that shows up about there. All right, so I've glossed over this issue of frequency, and I just want to come back to that for a second. All right, so let's come back to our carbonyl as sort of the archetype for IR spectroscopy. So 1700 cm to the negative 1, the term that we use for this unit, cm to the negative 1, is wave numbers. And so what do I mean by wave numbers? So that's our V bar, nu bar term. So what do I mean by wave numbers? Well, wave numbers is equal to waves per centimeter. So in other words, when the light travels 1 centimeter, you have 1700 waves. Well, if you have 1700 waves per centimeter, then your wavelength is 1/1700th of a centimeter. That's your lambda value, and that's equal to 5.9 times 10 to the negative 4 centimeters, or 5.9 microns, 5.9 micrometers. Now, you typically run a spectrum from, say, 4,000 to 600 wave numbers. That's sort of where a typical IR spectrometer works. So you're looking at the 4000 end from about 2.5 microns to about 17 microns. If you ever grind a sample to make a KBR pellet, and you don't grind it fine enough, you don't grind it so your particle size is below about 3 microns, then the light at the shorter wavelengths is going to get scattered and not absorbed by the particles. And this is actually pretty common. If you don't do a good job of grinding your sample, you're going to lose the CH region of your spectrum, right? Because that's at like 3,000 wave numbers. So that's at like 3.3 microns. So if your particle size is bigger than 3.3 microns, you won't see your CH peaks, and you'll say, my gosh, I make a compound, it's got to have some CHs in it, but I don't see the peaks. All right, let me, at this point, take one moment to talk about the instrumentation. So the instrumentation uses an infrared spectrophotometer. And I'm going to show you two real flavors of this instrument, but first I want to show you a fake flavor of the instrument to get it in your mind. In the simplest concept, so this is only a concept, in the simplest concept, what you are doing is generating IR light, meaning heat, wavelength light, from a glowing coil. It's passing through the sample. It's getting absorbed at different frequencies. You are breaking up the light with a grating or prism. And again, this is a schematic, an oversimplification. And you are detecting it. At the simplest level, you are simply looking at what light of what frequencies is being absorbed. In practice, there are many implementations of this idea. The simplest is a double beam instrument. In a double beam instrument, you're actually comparing the amount of light going through a sample and the amount going through a reference. So you have a source. The source is going out through a sample and a reference. It's coming to a mirror that's allowing the two to be compared. The mirror is going to a grating or prism. And that's going to the detector. And there are still some of these instruments in the department. All right, that is still easy to understand conceptually because it is the exact same concept as my gross oversimplification here, making up for the reality that your cell may absorb light, that your source doesn't produce the same intensity of light at all wavelengths, and so forth. Now, the instruments that have become very popular are FTIR instruments. And in an FTIR, it's a little bit more complicated, but the ideas are the same. The big idea you need to absorb is the idea of interference. And if you don't completely get it, you're still fine. You have a source. Your source produces light. You have a beam splitter. And what the beam splitter is going to do is it's going to allow half of the light to go one way, half of the light to go another way. So you have half of your light come up to a fixed mirror, and half of the light goes out to a moving mirror or variable mirror. And the variable mirror rides on a piston. And what's happening as the mirror is moving is different wavelengths at any given moment are getting interfered. Some constructively, some destructively. So in other words, as the mirror moves, the mix of light, it's no longer white light coming out of here. It's white light in which certain frequencies have been removed, certain frequencies have been enhanced by interference, and those frequencies are varying. Your light goes to a sample, it goes to a detector, and it goes to a computer, which takes the interferogram, which basically is the position of the mirror, and works it backwards so you get out the strengths at various frequencies. You will typically run this with a reference. All right, I want to take one last moment, and I apologize for going over, just to talk about sample prep. And I want to give you my personal take on this. This is a little separate from what you'll see in the book. All right, IR has changed a lot. Back in the days where NMR barely existed in the 1950s and 60s and even into the 70s, JOC, Journal of Organic Chemistry, wanted people to report every peak. In other words, you were creating a fingerprint for a company because you didn't have a lot of other data. Nowadays, JOC says, look, tell us about the functional groups in your compound. Report just the important peaks. And usually that doesn't even mean CHs in your sample. It usually means carbonyls and double bonds and alcohols and nitriles and triple bonds and so forth. And that's the question you're typically asking when you're carrying out a functional group interconversion. You're probably not looking for aromatic CHs or aliphatic CHs. You're probably looking for alcohols and carbonyls. So make it easy. All right. One of the techniques, the reason people don't want to run IR is it's a pain in the neck to make. Making a solution is easy. You do it for NMR. No one complains about doing NMR. I'm a big fan of solution IR. Again, if you go back to the old days, you would use carbon disulfide and carbon tet, so you would get every peak clear. Isn't working. 5% solution in chloroform in CH, pardon me, Cl3, you'll lose a couple of bands in there. You'll see some blackout regions. So you lose the bands of chloroform at 775. Typically, if you're using an FTIR, you'll see very strange patterns associated with interference here, where just no light is getting through. But that's super, super easy in a 1%, in a 0.1 millimeter cell. Now, my other beef about IR, and this comes from being a PI who's bought far too many sodium chloride cells, is you get one person who gets the cell wet and they've clouded the thing. I am a huge fan of calcium fluoride cells. I've used this in my synthesis lab class for undergraduates. We bought 2 of these cells and I expected them to get broken with a bunch of undergraduates using them. They've been using them for a couple of years now. Calcium fluoride doesn't dissolve in water. If you get water on it, it doesn't hurt. The cells cost a couple of $100 a piece. Some of the TAs in the course told their PIs to get one, their advisors to get one. Calcium fluoride cuts out below 1,000 wave numbers. In other words, you don't get light through it below 1,000 wave numbers. But that's no big deal because, as I said, we're going to concentrate on functional groups. You make up a couple of tenths of a mil, inject it into the cell. Everyone knows about KBR. Who hasn't made a KBR pellet? Who's enjoyed making a KBR? Okay, a couple of you. Great, grind your sample fine. If you're making KBR pellets, I'm a big fan of a ball mortar called a wiggle, which you use in a wiggle bug, which is a dental mill. You shake it up, 1 mg KBR. One big sample per 100 mgs KBR with lots and lots of pressure in the cell. Just grind it fine. Another one that you probably haven't seen is a neutral mole. Mole is just a fancy word for suspension. Neutral is a fancy word for mineral oil, which is a fancy word for hydrocarbon oil, alkane oil, that has those bands I talked about at 2850 and 2920 and 1380 and 1465. You just take 3 mgs of your sample, grind it up in a mortar and pestle, or I am a big fan of frosted microscope slides. Grind it together 10 seconds with a teeny tiny drop of oil, scrape it onto a salt plate, and you get a spectrum that has your CH bends and stretches. But that's okay, you just ignore those for the oil, and you see your functional groups. Anyway, that's my take. We will talk about spectra and functional groups next time, and I will see you on.